Okay, so this is going to be acidity. Now, there's a few different concepts you can use to predict acidity, okay? But overall, the biggest trend typically revolves around how much electron density there will be, okay? So remember, the stability of the base is the strength of the acid, okay? The stability of the base is the strength of the acid, okay? So if your base is very stable and the H plus will not go onto it very easily, so it's very stable having a negative charge, then that's going to be a very acidic compound, okay? Because it'll lose its H plus very easily, right? Think of it kind of like this. If you're a millionaire and you lose $100, probably not going to bother looking for it, are you? So that $100 can build up around that millionaire quite a bit, and that's why they have toadies. Groupies, people that follow them.
A very basic solution, or a very basic stable base, is a very strong.
Is a strong acid. Okay, so for example, we have HCl. Okay, so if the H plus comes off, that is acting as an acid, right? What if the Cl minus was not stable, was very reactive? It's going to attack the H plus, right? And then it'll take it right back on. So that would be a very weak acid, wouldn't it? Because you'd have very little H plus coming off.
Because acids want to get rid of the hydrogen.
Exactly. You have to be able to lose the H plus. Because that's the definition of an acid, right? Losing that H plus. Okay. So let's go with Cl minus. Cl minus is actually very stable as a negative ion, right? And we see that everywhere. We have NaCl, HCl. Cl minus is very stable. Okay? And that's because it's big. It can afford, and it's a halogen, so it can afford to have those electrons just floating around there, and it'll hold on to those electrons very easily. Okay? So it's a very, very stable base, the Cl minus. And it won't attack the H plus easily. The H plus comes off very easily. And so that is one of the strong acids, HCl. Okay? So remember, what you're looking for here is the things that can be negative and they'll be stable. Things that they are less stable when they're negative is going to be a weaker acid. Things that are more stable when they're negative would be a stronger acid, right? Okay. So, what happens to a carbon when you put a bunch of CH3s on it? Think about the electronegativity of a CH3. We have hydrogens, 3 of them. Hydrogens typically lose electrons very easily, right? Okay. Carbon would gain the electron density a little bit. Okay? Not a huge amount, it's not polar. But again, that carbon right here is going to be a little negative, isn't it? Okay? And then we have a carbon in between 3 of these. So that means this carbon here has quite a bit of negative charge around it, doesn't it? Again, the CH3 is going to be a little negative. So if you put a bunch of things that are a little negative around something, because the hydrogens are worse at keeping their electrons on them than carbon is, right?
Because the electronegativity of the carbon is higher.
Yes. Yep, the electronegativity of the carbon is higher than hydrogen, right? So that tells you that the electrons will spend more time on the carbon. Okay?
So that makes the carbon more electronegative?
Yes, the carbon is more electronegative than the hydrogen is. Okay? And this carbon in the middle here is surrounded by 3 things that are all a little negative, aren't they? And so that carbon in the middle is going to be a little bit more negative than it normally would be. Okay? It's going to have a bit more electron density than it normally would be. Make sense so far? Okay. So if you put a negative charge on this, ideally you would want something a little positive over here, right? But you have something that's a little negative over there, don't you? So that means this is going to be less acidic. It's going to be less stable with a negative charge. Did that make sense? Okay. Notice that this one you've lost one of those carbons, haven't you? Because again, as you go along this chain, that's going to have less and less effect on this one, right? You know, how much does it affect you if somebody over there spills something? Nothing. Somebody on the other side of the room spilling something doesn't do anything, right? But if somebody next to you spills something, you're going to get a little wet, right? Okay. So again, the same thing here. If it's here, okay, that might affect me a little. If it's all the way over here, almost no effect, right? And if it's even further out, no effect at all, right? Yeah. So this is insignificant effect. This is nothing. Just not even worth talking about. Okay? And the next position over, which would be the alpha position, that would be, it has an effect on me. Okay? Okay, so here we have two CH3s. That means that this is going to have some negative charge to it, a little bit, but not as much as this one, right? So this will be more stable if this has a negative charge here. Okay, that makes sense so far? We look here and it only has one carbon attached, doesn't it? Yeah, so this is going to be even more stable.
More stable means it's going to be a more
Stronger acid. Yeah. More stable with a negative charge, i.e. more stable base, gives you a stronger acid. Okay. What about the other way? So the strength of a base would be what? Well, yeah, it's how weak the acid is. That's one way of saying it. But the strength of a base would also be the stability of how stable the base or the acid is. Yeah. Yeah. So if an acid is very stable, having taken on an H+, that makes it a very strong base. Remember, every time you're talking about acids and bases, so the base has to fall apart to make an acid. See what I'm saying? It's always reversed, right? Stronger an acid, the weaker a base. Another way of saying that is the stronger an acid, the less stable, more likely to fall apart the base is.
So the more stable an acid is.
Acid.
Or, yeah, the more stable the acid is, the stronger the base.
Reverse.
The opposite of that.
The opposite.
Okay, the stronger the acid is, the weaker the base. And the less stable the acid is, the stronger the base.
Again, you're okay. Okay, so yeah. Well, okay. So the less did you say the less stable the acid, the stronger the base? Yes.
Okay.
Yes, because remember it's falling apart.
Yeah.
Okay. The more likely to fall apart the acid is, the stronger the base. The more likely to fall apart the base is, the stronger the acid.
So like that part right there, we didn't do anything, we just had to kind of look at it, and then we should be able to like, okay.
Well, we did reasoning, yeah.
Right.
And that's all we had to do. It was just reason out, hey, this would be less stable. This would be more stable with a negative charge. The base would be more stable. Or less, okay. The base would be less likely to take on an H+. Let me rephrase this, because it just makes more sense. So the less likely the base needs to take on that H+, the stronger the acid, right?
We don't need the H+. Because acid will be really.
So what we're looking for is the more likely it is to stay together, then the other thing will be more likely to stay apart. Is that making a little more sense, maybe? of saying that is we're looking for something here that this negative charge will be very comfortable staying. Because remember, if it's a strong acid, it loses the H+.
So how would you like? Okay, I understand what you're saying. Now, how do we take that into like these like this like first
Okay, let me ask you a question. Let's look at all these things. Let's just look at one of these, okay? We have one of these, it only has one oxygen on it. We have another one that has 2 oxygens on it. And we have another one that has 3 oxygens on it. Which one will be the strongest acid? The one with the most oxygens. Why is that? Yeah. We have more oxygens to hold that negative charge on, right?
So more stable.
Be more stable. And so that means it's a stronger acid, right?
So say a molecule had, like say it was an oxygen and it didn't have any other oxygens, and there's another one that didn't have any oxygens, would they be equal, or would it just kind of like what the other electronegativities are?
Okay, so these are general guideline rules. Yes, it gets more complicated when you start having not obvious electronegative groups, okay? So if you have things that don't have any oxygens on them, it starts getting a little more complex, okay? But essentially almost all organic acids are like that. We will go into more details, though, on some different acidic groups. For example, a carbon-carbon single bond, the hydrogens on this are very, very, very low acidity, okay? They essentially don't come off, right? They're very low acidity, right? However, if we were to look at the hydrogens like here, next to this very electronegative group, right? This hydrogen that comes off here would be more acidic.
Because all the electron negativity is going towards the oxygen.
Exactly. Exactly. So this hydrogen, if we lose this H+, right, it would leave a negative charge. This negative charge is going to be more stable because it can flow into this group right here, right? That can share it. Is that making sense?
Yeah.
Okay, very good.
So if we do number 13, now let's take a similar problem, but I think it's only, I think number 13.
13?
It's just it's
Yeah, let's go ahead and do it. All right, you said 13.
Really?
Yeah, I've had students both come in crying and break down crying. So. I've had both ways. Where people come in crying, they stop. Well, actually, nobody has left my office crying, so that's yeah, that's good.
I be the first.
Yeah, you can be the first.
Sweet. Get the Hall of Fame board ready out.
I mean, I'm not trying to make this hard for you guys. It is a harder topic. This is a junior, senior level course. We're building up to the big boy stuff. They're the big girl stuff. Either way, it's not the kiddie stuff anymore.
I like this better than I like Gen Chem. Oh yeah, me too. The only reason I say that is because Gen Chem had a lot of math.
Yeah.
And I, not saying I'm bad at math, but it was not, it was made it more difficult. This is more like concepts. Once you understand the concepts, then you can do really anything.
Mm-hmm.
And so that's just like getting the concept. That's the hard part.
Okay. Okay, so here we're looking at the acidities of these different compounds. Under most definitions, does this specifically say anything about Lewis acid base or anything? Nope, don't look like it. Actually, it has hence here. Yeah, but it says the same thing I've been saying. Yeah, that's funny. Anyways, okay, so there's sort of two things you got to think about here. Since it didn't mention Lewis acid bases, you're actually free to use sort of any definition, but they all work out the same, okay, in this case. However, if you're not looking at, well, even if you're looking at Lewis acid base, Bronsted-Lowry acid base, or Arrhenius acid base, you'll notice that none of these are typically what you think of when you think of acids, are they? See that? There isn't even an acidic hydrogen on most of these. So most of these are not what you consider typical acids, right? And so what they would normally be considered is, these would be what we normally consider bases, huh? Yeah. Okay, especially this one. This one's a very good example of a typical base, right? Okay, so, well, if you have a stronger base, then what would that be for acid? Yeah, it'd be a weaker acid, right? Or less acidic. Yeah. If you have a weaker base, that would be more acidic. Yeah, you got it. And so that's the first thing you got to connect, is you're not really talking about acidity, but yes, you can relate it to acidity. We're really going to be looking at basicity. But again, same difference. Just opposite, inverse, right? Okay, so what we're going to be looking at here is what is the most likely to act as a base? Do you guys want to talk about these in Lewis acid base or as Bronsted-Lowry acid base? Either way would do the same thing. Work either way. Lewis? Sure. It'll make it a little bit more difficult to talk about unless you got the Lewis acids bases down pretty well. But you should. Okay, we're talking about Lewis. Okay. So what's a Lewis base?
I am a sophomore. I'm doing organic chemistry as a sophomore.
I'm a senior, you know. Come on now. You're good.
Exactly, so we're all opinion.
A Lewis base, is that what you asked?
Yes, what's a Lewis base or a Lewis acid? Either one would.
A Lewis acid is willing to give up hydrogens, and Lewis base is willing to accept them.
Lewis has absolutely nothing to do with hydrogen. Yes, you got it. So a Lewis base donates electrons. A Lewis acid would be an electron acceptor, right? Okay. Okay, so what we're looking for here is if we're a Lewis acid, we're better off accepting electrons onto us. If we're a Lewis base, or less acidic in this case, we're going to more easily donate electrons. Okay? Okay, so do you know what ME is? Has nothing to do with the periodic table. Nope, not on the periodic table. If you watch the lectures, you should know. It's methyl, chapter 1 lecture. It's methyl.
Oh, yeah.
ME, abbreviation for methyl. So that means that's a CH3 group, methyl. So we have two CH3 groups on here. Okay? This one has one CH3 group. Okay. Okay, so if you donate electrons, this actually ties just into what we just talked about earlier. You're going to probably end up with a what charge?
Positive.
Positive, right? So you have electrons spending less time on you. Okay? So if this donates electrons, you'd end up being positive, right? Would this be stable or not stable with a positive charge there?
Stable.
Yeah, you have these two methyls to donate electron density to you, stabilize you. You have this one that can donate a little bit, but you have an even bigger thing going on here.
Oxygen.
Yeah, the double bond oxygen, right? We've seen lots of cases where this double bond oxygen moves into here and, the electron density stabilizes that. Again, in that case, one of the big things I want to point out here is lone pairs, pi bonds, these are delocalized electrons. That means they can very easily get sucked up when you have like positive charges next to them, okay? Because they're delocalized, they flow fairly easily. That making sense? Okay. How about that one? Would this be able to donate electrons fairly easily?
No.
Not as easy as that one, right?
It can,
But this oxygen here could still do that, right?
yeah.
So it's not as basic, or another way of saying that, it's more acidic.
What do you mean by donate electrons? Like, I know what you mean, but like, why was that one? Because of the oxygen.
Okay, so think about it like this. All right, let's not do the Lewis since you're, you need to retrain yourself on the Lewis acid and base. Trust me, it's a very important concept in organic. Let's go ahead and step back to Bronsted-Lowry, okay? That's the one most of you are probably the most familiar with. That is a base would be an H plus acceptor, right? You can take on an H plus. An acid would donate an H plus. Okay. Okay, so in this case, this nitrogen here has a lone pair. It could very easily accept an H plus on there. That would put a positive charge on here, right? If it accepts an H plus, it's going to do that by taking that lone pair and making a bond, right? By the way, that's how that comes together. Like a Lewis base can donate an electron pair, can donate a lone pair. And so a Lewis base is, in this case, the same thing as Bronsted-Lowry base, isn't it? Yeah. You're just looking at electrons, right? For Lewis. Okay. So, yes, this one could very easily take an H plus onto here, right? And again, it would be stabilized by these methyl groups. It would be fairly good because nitrogen does that a lot anyways, right? Because it has a relatively low electronegativity, so it doesn't hog its electrons that much, at least compared to oxygen, right? Yeah. And you have this oxygen with this double bond, that the double bond can move in here and stabilize any positive charge. Okay? So that one's actually a pretty good one. Let's look at this one though. So again, we have an H plus coming on here. It being able to easily take an H plus means it's the least acidic, right? Because being acidic means it would donate the H plus, right? The H plus has to come off. Okay. This one right here, I mean, it still could, right? This oxygen here could still take on an H plus. This methyl group would help, stabilize it. That's cool. The double bond can still come over and stabilize it. So, it's not a bad base. It has some basicity to it. Yeah, so it's the middle, right? It's moderate. It's just not as good as the other one. Okay? And so it is more acidic, right? Because base and acid is opposite. Okay, this one right here, well, you have a hydrogen here. That's not going to do anything for you. Methyl group, that's not going to take on H plus. So really the only place you could take on H plus is this double bond oxygen, right? Which could, yeah, you could take on H plus, but there's just not anything to stabilize it, is there? I mean, you have a methyl on this carbon, and that's it. That's not a whole lot of negative charge to help you stabilize a positive charge, is it? Yeah. So that doesn't have almost anything to stabilize it. It's going to be pretty miserable as a base, isn't it? Yeah, so it'll be more acidic. None of these are acids by any stretch of the imagination. They're all essentially what we would normally consider bases in Gen Chem. Yeah. In organic chemistry, we're in this position where, first off, strong acids aren't even organic molecules for the most part. So, yeah, mostly you just use those to cause reactions. So really, when you're talking about acidity versus basicity, we're going to go beyond the pH 0 to 14 scale in organic chemistry. Okay? We will talk about acids that are negative 11. We will talk about acids that are positive 20. So their pH is 20. And this is acidic. Okay? I mean, 7 would have been neutral normally, right? pH 14 would have been the strongest base you could get in water, right? And so pH 20, this is our acid. That's pretty acidic. So we're talking about some things that are less or more acidic, right? Not in the purest sense acid-base. And that's because we're no longer going to be in the water scale. You guys know 0 to 14 is due to water, right? It's because everything's reacting with the water. And that's why a lot of organic chemistry, we can't do it in water. You have to make sure you don't have water. Very good. That making sense? Okay, did I go way too far into that? No. I lose everybody? A little bit. Okay.